Hello students, in this video we'll discuss several functional identities for the Riemann Zeta function. Let's recall, we have our Riemann Zeta function, which is zeta of z is the sum, n goes from 1 to infinity, of 1 over n to the z, right? And we know this converges, is holomorphic in the set of z such that the real part of z is bigger than 1. We know that it has a pole at z equals 1, and we know that we can extend it to the whole complex plane to be meromorphic with poles at 0 and 1. And we know that we expect zeros to be on this critical line, the real part of z is equal to 1/2, although that's the Riemann hypothesis. We don't know if it's true or false yet. Okay, excellent. That's the Riemann Zeta function. Let me do some formal calculations now. So here's the first formal calculation. Let's look at zeta of z quantity squared. If I square the Riemann Zeta function, what's going to happen to this over here? Well, this is going to be what? This is going to be the sum, n goes from 1 to infinity, of 1 over n to the z. And then I have another identical copy of this. The sum m goes from 1 to infinity, of 1 over m to the z. Right? If I assume that the real part of z is bigger than 1, both these series over here converge absolutely uniformly, so I can form their Cauchy product, right? So their Cauchy product is the sum m and n go from 1 to infinity, of 1 over mn to the power what? To the power z. Excellent, okay? Now I'm going to re-index this. I'm going to say that this is really the sum. K goes from 1 to infinity, and then the sum of what? M times n equals k. Every time that m times n equals k, we'll put a 1 over here, right? And then we'll have a 1 over k to the power of z, because m times n is equal to k, right? And so what is this over here? So let's examine this function over here, this sum over here. This is equal to 1 whenever m times n is equal to k, right? So let's do some particular values. So if k, for example, so let's set tau of k to be the sum over all m and n equal k of just 1, right? Where m and n are integers, right? M and n bigger than or equal to 1. What is this thing counting over here? So if k is equal to 1, m and n both have to do with 1 is equal to 1. If k is equal to 2, you can have a 1 and a 2 or a 2 and a 1. There's 2 of those things, right? If it's equal to 3, you can have a 1 and a 3 or a 3 and a 1. There's 2 of those things as well, right? If it's a 4, you can have a 1 and a 4, a 4 and a 1, or a 2 and a 2. There's 3 of those things, so 1, 2, and 4. Oh, this is just counting the number of what? So this counts the number of divisors. Of k. And so we've just shown over here, that zeta of z squared is really the sum, k goes from 1 to infinity, of tau k, the number of divisors of k, over k to the power z. Beautiful. That gives us our first functional form for zeta, right? Let's look at a next formulation of this. The next formulation would be, let's consider 1 over zeta. Okay? Well, that's going to be what? That's going to be the product over p prime. Not 1 over 1 minus p, but just going to be a what? 1 minus 1 over p to the z. Okay, cool, right? And that was the reciprocal, right? So of course, that's a negative over here. So now I just get the reciprocal of this over here. Excellent. So what's going to happen now? What's going to happen is I'm going to get what? I'm going to get the positive z now because it flips the sign. Good. So what's going to happen to these things over here? What sorts of terms are we going to get? We're going to get all the sum over all of the numbers k, right? K of z. And just the what? This is going to be equal to something. It's going to be equal to the sum k goes from 1 to infinity of mu k over k to the z, like that. Great. And so now what? And so now, what's this going to be? This is going to tell me what? What's this mu k going to give us? This mu k is going to be what? Well, if k is equal to 1, then what do we know? If k is equal to 1, I'm just going to get a 1. So it's equal to 1 if k is equal to 1. And now if I have distinct primes, right? So if K is a product of distinct primes, so if K is a product of distinct primes, P1 through PL, and these are distinct, well, if it's a product of distinct primes, I'm going to get what? I'm going to get you to -1 to the L, -1 to the L, because I'll have L terms and I'll have L negative signs. And then what happens if you're a what? If you're not distinct powers, right? It's going to be 0 if K is a what? It has a square prime. I'll say else, right? 0 else. There's no room in this, I can't have squares in this formula, right? There's no room in this formula for squares, so there's no squares of primes in this, which means there's 0 on those things over here. And this function over here, this mu, is called the Mobius function. Excellent. All right, so that gives us a formula for 1 over zeta. Now there's one last formula we'll talk about today, and that's this one. Let me consider zeta of z times zeta of z minus 1. Let's do the product of these things. What will this be? This is going to be the sum. N goes from 1 to infinity. 1 over n to the z. The sum m goes from 1 to infinity. 1 over m to the z minus 1. Like that. Okay. Now multiply these out. This is going to be the sum. N and m go from 1 to infinity of a 1 over m times n, m to the z minus 1, n to the z. And then we're going to do the same thing we did above over here. So by above, this is going to be equal to what? This is going to be equal to the sum. K goes from 1 to infinity. The sum n times m is equal to k of what? I'll have a 1 over what? So I need to have a factor of k. So this is going to be a k to the z. So we're going to pull out a k to the z, 1 over k to the z. But what did I have left over? What I had left over is I had m to the -1, so I really had an m, right? So what was m? So m is going to be what? M is going to be, so I have an m to the -1, so I'm going to put the m on top over here, just the sum of m over here. And now let's examine what that's going to count. That's going to sum up the what? That's going to sum up all the divisors of gut, k. So here that's the note. So note, if we look at this sum over here, if I look at it, so let's call it over here sigma k, which is the sum over all n times m equals k of just m, right? What's that doing? That's adding up all of the divisors of k. So this function, sigma k, adds up all the divisors of k. And so what's this going to give us? So this is going to be the sum. K goes from 1 to infinity of what? Of sigma k over k to the z, right? And that's our formula for what? That's our formula for zeta of z times zeta of z minus 1. So what's happening over here? When I look at functional properties, the functional properties of the Riemann zeta function, like zeta squared or 1 over zeta or zeta times zeta minus 1, what's happening is we're getting these number theoretic or these arithmetic functions. We're getting the number of divisors. We're getting the sum of the divisors. We're getting this Mobius function for that. It tells you when, if you have a square in your prime decomposition, it gives you 0. If your distinct primes, it gives you -1 to the number of primes you have, right? So we're getting these number theoretic functions, these arithmetic functions that are embedded in the Riemann zeta function. So it shows the close connection between number theory and the Riemann zeta function. Thank you very much.